Okay. So, two different versions today. We're going to be looking at the standard forms in the formula version and the standard form in the picture version. We're going to be applying the ideas we talked about yesterday with things like amplitude, period, phase shift, and midline in the formula, as well as what they look like to the picture themselves. For a lot of these pieces, it's helpful to draw a little quick sketch that compares before and after so you can see how they affect each one of these. Let's start off with the formula. Now, third column. Let's see. Period. We have amplitude. We have the midline. I would give just enough space to draw a little picture next to each one of these. And a little space for a little formula next to each one of these. So yeah, give it a little space. Give it a little space. Midline and phase shift.
Between the words and what?
You want enough space here on the right for each one of these. We'll draw a picture for each one. Here we go. The formulas are relatively simple. There's just one for each one of these. So, for example, the period. Determine what's going to happen to the period. For these ones, it is 2 pi divided by the absolute value of b. This is the formula. The whole thing. This will determine how the formula changes the period. Remember from yesterday, the period is how long it is before the next repeat. So what I'm going to do is I'm going to pull up Desmos. I'm going to start by just looking at the standard sine function. And we're going to see what happens if I adjust the b value to the period, how it changes over time. We'll take a look. First, let's start with the basic sine function. So this is sine. Here's what it looks like. I know. It's beautiful. I drew it myself. Now let's make a change. Now this formula only affects b. So I'm only going to change b, the number in this case attached to the x value. So what I can do is I can change it by saying, instead of being x, maybe I make it 2x. What this is going to do is going to affect the period, how long it takes before there's a repeat. Now, according to this picture, the normal period is from 0 to 2 pi. If I make b a 2 now, the new period is found by plugging into this formula. One more time. If I plug in a 2 for b, the new period is found by plugging in that 2 here, outputting the new period, how long it takes before that thing repeats. So normally, 2 pi. If I put a 2 in for b, my sine becomes sine of 2x, and the period changes. Now it repeats much faster. That is because the period has been made shorter. So it repeats more often. Now, instead of starting at 0 and ending at 2 pi, now one cycle only takes a single pi for that blue line. Again, instead of originally starting at 0 and ending at 2 pi, now one full cycle takes only a single pi. We've taken the period and shortened it from 2 pi to 1 pi. We've cut it in half. Adjusting the b value changes the period. Now, the bigger I make the b, the more it's going to change the period. Let's say I do 3x. Again, I can find the new period by plugging 3 into this formula. Now it's going to be how long it takes to get to my next change. So instead of 2 pi, it's not going to be even faster. Now, to complete one cycle, which remember, according to our picture, one cycle is one loop up and one loop down. Now the period is only 2 pi over 3, a shorter value. Because I have changed my b, I have shortened how long it takes to do a repeated cycle. Again, original one started at 0, ended at 2 pi. Our new version, by just adjusting the b value, now starts at 0 and ends at 2 pi over 3, which is again, if I plug in 3, tells you exactly how long it's going to be. So, this is how we change that wavelength, what's referred to in physics. We adjust that b value. Again, the bigger we make it, the more this changes. If instead of 3, I made it 10. Now it looks faster. Now to complete one cycle, come on, zoom into it. There we go. To complete one full cycle, only takes pi over 5, which is again found by putting 10 into this formula. So again, we adjust it by looking at how long this actually takes for it to happen. Now, if you're given the formula, finding the period is very simple. You plug B into the formula, you're done. If you're given the picture, though, there's still a way to find the period. A very simple way, but you have to know two things. You have to know where the function starts and finishes one cycle. If I want to work backwards to find the value, to find the period, the easiest way is to know where one cycle starts and one cycle finishes. And it doesn't matter which cycle or even which part of the cycle you choose, as long as you match cycles. Example, if I start from here to there, this is the same period. It's the same amount of time to do one cycle as it is from here to there, one cycle. It's the same amount of time. It's consistently the same because, again, it's a periodic function. So it always repeats after the same amount of time. So it repeats by pi over 5 here. It's going to repeat by pi over 5 here. And going forward. Every pi over 5, it will repeat. So again, this is the period. It's how it functions and changes over time. You can determine it easily by plugging into the formula. If you do not have the formula, the best way to find it is the absolute value of the end of one cycle minus the beginning of one cycle. Now, this to work, you have to think of it one cycle only. If you accidentally click or select two cycles, this won't work. You just take the end number minus the beginning number.
So that's on picture.
Yeah. So let's say, example, okay. Now I don't have the formula to work with. How do I determine what the period is? Easiest way, select one cycle. From the beginning of that cycle, find the end of that cycle, subtract the two values. And you will always tell what the period is. And again, it doesn't matter where. Obviously, the first one should be the easiest one, because one of the values should be 0 or near 0. But you can do this anywhere. Example, this period, I can choose that one cycle. All I have to do is take pi minus 2 pi over 3, and I have the period. Alternatively, I could take from here to there, negative 2 pi over 3, negative pi over 3, I get the same period. So again, I'm doing one cycle. One start, one finish, subtract the 2, you'll always have a period. The reason I'm emphasizing both is because in your homework there's both types. Sometimes you'll be given the picture, sometimes you'll be given the formula, and both will say find the period. So you need to be prepared for either one. The formula is easy. Take the values and plug it into this formula. 2 pi over b. So how do we find it? You take 2 pi, plug in 6 for b. So 2 pi over 6, which is pi over 3. How do you get that from the picture? Same thing. Start of one cycle, end of that same cycle, subtract the 2, you still get pi over 3. So, if you're given the formula, how do you find the period? Formula. If you're given the picture, you have to look for pieces in the picture that stick out. Next one, amplitude. Amplitude is how high up or down your function changes. The minimum versus the maximum. Now, in the formula, absolute value of A is your amplitude. Notice I'm using absolute value a lot. That is because in most cases we talk about them as always assuming to be positive numbers. If your period is negative, that indicates you're going backwards. Be awkward. So, let's talk picture. Again, here's my original function, sine. The amplitude is how far it extends up and down. If I change that number out front, that's going to change my amplitude. How far it extends up, how far it extends down. Let's try. Here's sine. I changed the number out front. Let's make it a 3. It takes that red line, stretches it up and down. We've changed the amplitude. We've changed where the top and the bottom of this function is. And it used to stop at 1. Now it stops at 3 and -3. We've changed the height of this function. Now, again, with the formula, that's easy. It's just the absolute value of a. So the number out front's a 3, then the amplitude is a 3. The number out front is 7, the amplitude is a. Very simple. If the amplitude is the number out front is a -4, the amplitude is a 4. Again, it's how the absolute value is. In the picture, there's a simple way to fix this. Before we do that, let's look at some other options. Again, the best way to think about this is always think what the original function looks like and then make a comparison. Is it taller? That must mean the amplitude's been changed. Is it shorter? That means the period has changed. Is it stretched out? That means the period has changed a different way. There has to be some change to this function. Let's make it bigger. Notice now, that function is fluctuating back and forth with the top and bottom of 12. So notice it's still taking 2 pi to go through one full cycle. But now the top and bottom have been stretched out to a top and bottom of 12, an amplitude of 12. So again, formula, easy. Picture, also pretty easy. Here we go. It is also an absolute value. It is the max minus the min. My picture here, if I want to figure out what my amplitude is, I can go to this picture. Boom. Now, the max minus the min will always give you too big a number. In fact, it'll always be twice as big as it's supposed to be. Is there one other change? Divided by 2. This will always determine the amplitude.
Can't you just look at the top number as the graph?
When we talk about these two, that method can still work. It's just a little less reliable. You'll see in a second why. So now I'm going to take this picture. I'm going to go with 2 steps instead of 1 change. Instead of just changing the amplitude and just changing the period, I'm going to change both. And you'll see it's going to take this function and make 2 adjustments to it. I'm going to either squeeze it together or slide it apart, left to right, or it's going to squeeze together and slide it apart, going up and down. But both changes are predictable because of how the function works, because of its standard form. If I change the number on the inside, it's going to change that left to right values. How long it takes to do 1 full cycle. If I change the outer number, it's going to change the up and down value. Again, how long it takes to do 1 cycle up and down. Let's see. Let's look at this one. So up here in red, you can see the original function. Up here in green, the new version. Even without the formula, I can see that I've made some changes to it. It's cycling faster. This indicates the period has been reduced. Therefore, there has to be a b value somewhere, which I can find by isolating 1 cycle and subtracting the values. Or if I have the formula, I can see a b value is 2. So my period has to be plugging in 2 into this function. So the period would be pi, meaning every pi this thing repeats. And I can verify that right here. Starts here, ends there. Every pi this thing repeats. Starts here, ends here. Another pi, another repeat. I can also see how the amplitude has changed. It's no longer isolated between positive 1 and negative 1. It's now isolated between positive 3 and negative 3. So the amplitude had to have been adjusted up and down. Again, Max minus min over 2. When it's centered, obviously you can just read it fast. But that doesn't mean it's always going to be centered. Let's start with the third change. Midline. The midline is based upon the d value. Yeah.
Is it not absolute value?
Nope. It is just a d. Insert terrible joke there. Say again?
It's not absolute value. It's going to go negative.
Correct. So let's take an estimation here. I'm going to get rid of 3. I'm going to get rid of 2. Now we talked about transformations back in September. Okay? It's been a while. Numbers inside of the function always change left to right. Numbers outside always change up and down. This d value, you notice, is outside of the function. So it's going to take this function and move it up or down. But which way? So I ask you guys a question. If I was to add 3 at the end of this function, so I change my d from a 0, which it currently is, to a 3, what's that going to do to my picture?
Move it up 3.
Move it up 3. Okay, the transformation. Let's verify. Plus 3. Oh my gosh, you guys are smart. Notice just putting the 3 there did not change anything else. But also notice, as we pointed out before, Garrett, now I can't just look at the top and bottom number to determine the amplitude.
Or you can look at like how far away it is.
Which is basically what you're doing here, right? So we can now make 3 changes. Now, obviously the plus makes it go up in value. We can assume then that minus is going to make it go down in value. Let's verify. Subtract 2. So it takes this function, moves the entire thing down 2. Notice the period is the same, right? This one starts at 2 pi, and it's still 2 pi. It still takes 2 pi of a cycle to repeat. We haven't changed the period. Notice the top and bottom are still have an amplitude of 1. I can see that directly with this version in red, because the top is a positive 1, and the bottom is a negative 1. With the other one, it's a little tougher, but again, my formula can tell me. The top is at negative 1, the bottom is at negative 3. If I plug those in, I will get an amplitude of 1, the same as I should. It always works that way. So, this means now we can make 3 changes to our function. I can take the function, I can stretch it left to right. I can compress it left to right. I can stretch it up and down, or compress it up and down by changing the numbers inside or outside the function. I can also move it up or down by changing the midline. Notice this problem, unlike with traditional functions, I remember seeing the midline because it's where the middle of the trig function is. Remember, everything cycles around that middle. It goes up and down from the middle. So the midline is really important, where the center of it is. Now, in the picture, how do we find the midline? If, for example, I give you a random one.
Where it crosses the y-axis.
A good idea right now, but you can best bet what phase shift is going to do.
Go to the left.
Because of the left and right. So right now that's a good idea. When in the second, probably not as good. How can we reliably find the center?
Move left and right.
Okay. There is a formula.
What's the formula?
Ready? To find this is where it gets interesting. Because these two are very similar.
Okay.
Add them together, divide by 2 instead of subtracting together. So let's look at where the top is. The top has a value of negative 3. The bottom has a value of negative 5. Add those together, we get negative 8. Divide that by 2, we get negative 4. Oh, my mistake. No absolute value. I always make that mistake. Just average them. Algebra 1. My gosh, I'm getting out of line here. It's terrible.
Oh, yeah.
I'm glad this is not my notes. Okay.
Jeez.
Beautiful, I know. I'll try to make a better version of this and post it in the Google Class.
No.
There is one in your book that is a slightly better version of this.
I can leave it. You don't like it.
Let everybody suffer?
Yeah.
I love it. That's my go-to move every day. Okay, the last one is called phase shift. So far we've talked about what A can do, what B can do, what D can do. C, as it turns out, can't work alone. It's shy. It's scared. C needs a friend. I'm going to first put the formula up here. And we'll talk about what it does. C over B. Now notice one thing real quick. This is where I get the most headaches. It is bx minus c. So if it's positive, the c is negative. If it is negative, the c is positive. That provides the single most headaches. It's because people misremember the formula. It is bx minus c. So what goes in here is the opposite sign. If it says plus 3, we plug a negative 3 into the formula. If it is minus 5, we plug a positive 5 into the formula. Let's watch. Again, I'm going to go back to the bare bones and see how this functions. Here we go. I'm going to start just by adjusting C. Because if I adjust C, the B value assumes to be 1. It's the number in front of the X. And what you're going to see is it's going to move this thing a little to the left or a little to the right. Take a watch. Adjust my C by saying plus 1. Look what it did. And it can be a little hard to see. So look close. The red number is the original function. The original function started at 0, 0. Red function. I might have. It's possible. I was thinking about working. The green function, notice, starts in a different spot. It starts 1 unit to the left. As you see is 1. Again, numbers inside affect things left and right. So the B value and the C value affect things going left to right. The B can affect the period. It can also affect the starting location. The C for sure affects the starting location. So, another change. Instead of plus 1, it's minus 2. This one starts 2 units to the right. It's the exact same picture, just shifted 2 units to the right. Now, this is where it gets kind of weird because it's a repeating function, right? It's periodic. So you have to look and see which one changed. Because if you look at this picture, I see it moving 2 units to the right. Somebody else might see it starting all the way over here, moving it much farther to the left, and giving it a weird value. So on one hand, I could say this has been shifted negative 4.283 to the left, or I could say it's been shifted 2 to the right. They're the same thing. It's a periodic function. Eventually, it's going to repeat. I could go even more extreme and say, hey, it shifted it all the way over here. Because they will do the exact same thing. To prove it even further. Sine. Now, 4.283 is a weird number. Notice these two look exactly the same. It is because of the fact that they're periodic. These two are separated by 1 period. Therefore, they will look exactly the same. let's backtrack.
Formula.
Make it even simpler. Here's my original function, sine of x. Here's my new function, sine of x minus 2 pi. They're the same. They are the same. Because they're periodic functions. Is just the way it works. Because eventually they will repeat themselves. There is often more than one answer to how this function looks. It is your job to decipher what you think the best answer, the most logical one is. I don't know about you, that one's easier for me to get right than the other one. And if you look back at the previous two, it's much easier for me to see this green version than to see that purple version, despite them being the same thing. One shifted 2 units to the right, the other shifted a weird decimal to the left. Same answers, easier one is probably the one I want to go with. So, when it comes to starting place, you always want to try to pick the best and nicest value you can. Now, I'll tell you from experience. In terms of the formulas, I've become a formula man in this chapter because everything is plugged into a formula and solve. I want to find the period, plug into the formula and solve. I want to find the midpoint, midline, plug in the formula and solve. Like, it's real simple. I've become a big hater of the picture version of these problems. Why? Because there's more than one answer many times. If you're like me in a lot of math, I don't like having more than one answer that's right. I like having one answer, one great answer that's amazing and wonderful. But you don't have the luxury here. These two are the same. Both are right. And there's more that are correct as well. You just gotta keep going to the right and keep going to the left. You'll find more examples. But
Let's get this formula.
the formula?
Yeah.
There isn't a good one.
I'm gonna, yeah.
There is not a good formula for the picture. The book even says, like, there's not a great way to find the phase shift from the picture. What's the best thing to do is to look for a starting place. Try to find that starting place. This is always the one we will do last because we can use everything else can be found with a different formula easier, right? I can find D using this formula very easily. I can find A using this formula very easily. I can find B using this formula very easily. These two, not so good. We will often do the phase shift last because it is the most complicated and has the worst method to do it. You've just got to look for a starting place, solve for B, then solve for A. That's right. You gotta first solve for the B, then work backwards to solve for the C. There is no great easy path to get to the solution there. Now, to showcase all these exact same things with cosine, I'm just going to do real quick all these exact same formulas with cosine. They work the exact same way. There's no change. It's just now going to be the cosine function that's making these changes. Take a look. So, just like before, let's look at the cosine function. Cosine of x. So in black up here, there's the cosine function. As a reminder from yesterday, it is an even function. It is periodic. Copying itself every 2 pi. Let's make some changes. Starting with the period. If I change the number on the inside, that will either shorten or stretch out left to right this function. Let's make it a 3x. It takes that period in black and squishes it together. Now instead of repeating every 2 pi, this thing repeats every 2 pi over 3. Again, I plug into the function 3, I get the period of 2 pi over 3. Again, every 2 pi over 3 repeats. It happens to the tops. It happens to the bottoms. It happens to the intercepts. As long as you find the matching piece. Every 2 pi over 3, there's another match. But make sure to match directly. I like to match tops because they're easy. I'll match bottoms. Again, they're relatively easy to see. I don't like to match these middle values when I can avoid it because I don't want to confuse this middle value and that middle value. These two are very different things. They're not separated by one period. They're much shorter. They're closer together than they're supposed to be. Remember, it's got to be one full cycle completed to create a period. I showed you with sine examples of a big number, like 3, 4, 5, 10, 20. I can stretch or compress these. If I get a number that's smaller, like 0.5 or 1/2, pull it out. Now, one cycle, instead of repeating every 2 pi, now repeats every 4 pi. Again, I plug in 1/2 in this formula, and I have my new period, how long it takes to repeat the cycle. So I can determine the period from the formula by plugging into the formula, or from the picture by plugging into this version of the formula instead. Make sure to match point by point. Next, amplitude. And again, the best way to see this is to have a solid picture in your head of what the original function looks like. Because I want to know if it's been stretched. The best way to know that is if I know what the original function looks like. If I know the original function looks like one thing and it looks more stretched than that, then I know it's been stretched by an amplitude. That's why we spent so much time yesterday going through what the original cosine function looks like, what this thing looks like. Because I can't understand that I made a change unless I have a good idea what that black function looks like. I look at it and go, that is clearly been stretched out. And that is harder to do when you don't have them in the same picture. You got to have it fixed here. You got to know that cosine starts at 0, 1, ends at 2 pi 1, follows that path, and if it does anything else, it must have had some changes made by this formula. And again, if the number out front is smaller, 0.3, it's going to make my wave smaller. Again, easy to see when you compare it to the original, but if the original's not in front of you, you got to look at it and go, that's smaller. Clearly. Because I know what the original one looks like. Max of positive 1, min of negative 1.
Basically, it's the same rules from algebra, like stretch, compression, all that stuff.
I wonder why we spent so much time talking about that in October. It's the exact same rules. Because those rules apply to any function, and cosine and sine are just functions. That was a fantastic thing to point out there. Thank you. The same rules that applied back in October apply over here. But we now are applying names to them. I'm guessing that's close.
Okay.
So, in algebra, when we stretched it out, we would just say it's a horizontal stretch. But now we say we are stretching the period. Now, in algebra, when we say we're doing a vertical stretch, now we're saying we have a larger amplitude. The reason why we have different names for them is because these apply to more real-world problems and real-world scenarios than typical algebra does. So when we talk about the amplitude, we're talking about how loud the music is, or how high the wave is that's about to hit your house. Okay? Talk about how long the period is, how long it takes to repeat that thing. Now I'm talking about a signal coming from a computer. How long it repeats can be the difference between it going properly and the computer working, or it breaking. So high information is really critical. And again, in algebra, you'd use words like vertex. The vertex is operating up and down, and left and right. And now we call that midline and phase shift. Again, we're applying terminology because we're applying them to something real. All right. Last thing. Let's put it all together. Our long-term goal by the end of class on Friday is to do two things. One, if I give you an equation, can you draw a picture? And two, if I give you the picture, can you tell me the equation? We will spend the next 3 days practicing this, each part. I'd suggest tomorrow, if you don't have any, bring graph paper. Reason being, it takes a certain amount of skill to be able to look at a picture or a function like this one, where I adjust more than one thing. Let's say I make this 2x, 2 minus 3. And to know how that's going to change this black line into the blue line. How do they do it? Well, we change the period by cutting it in half. We doubled the height by changing the amplitude. Moved it 3 units down using the midline. And you can see all of those in the picture. The height used to be top of positive 1, bottom of negative 1. Now it's separated by 3. Top or 4 units. The center, all the way down to. We're going to practice this. We're practicing this week. With 5 minutes left in class, are there any questions about today's material? This, by the way, concludes our notes this week. The rest of this week is working on problems and trying and learning how these fit together. So, that is the note for the week. Any questions? Okay. Tomorrow, we'll start attempting to take these functions. We'll start graphing them and reverse engineering the formulas using a graph. Come with a piece of paper, ready to play tomorrow. Oh, play is a relative term.